one more. All right, I guess that's how we're gonna start. Good morning, everybody. Oh, there she is, as soon as I click the button, every time. All right, good morning, everybody. I've got what I hope to be a most interesting, thought-provoking class for you today. So, and luckily, unlike Barrett Wallace's mission here, it should not require any actual sacrifice. What we are going to talk today is kind of a switching of gears. We've been running with these rational functions for quite some time, and we're going to finish up with those kind of in the back of our mind, right? Set them on the back burner, and we're going to start cooking up something new. But we're going to borrow from the rational functions. They will make for a great example of the application of this new idea. That idea is limits. What is a limit? Why is it important? Why is it significant? It's going to be the foundational big idea of calculus, or at least one of. And way back when, on a Friday, we watched a video about the basics of calculus, and it was that idea of studying change, not on an average large scale, but zooming way into an infinitesimal tiny point. What is the change at an instant? How is something changing? And the only way to do that feasibly was with limits. Now, what we're going to begin today is just a broad scope overview. What are limits and how are they useful? So I've got a few bullet points here I'm going to talk a little bit about. And then what I actually have for you is a song, one of my favorites, from the Calculus the Musical. That's right. There is a Calculus the Musical. It's fantastic. If anybody likes musicals, it's just as wonderful as any other. They actually, there is a traveling theater troupe that goes about the country and performs this musical. You can also buy their music online. And they actually came and visited my high school when I was there. And it was a wonderful experience. And I have found that just about all of at least the basic concepts of calculus, not like the specific formula in a particular problem, but the concept, all the ideas of calculus, I keep in my mind by knowing these songs. So I'm going to share with you the first of many. We'll definitely get to far more of them next semester. I'm getting ahead of myself. What are limits? Limits are the almost but not quite. Hence the title here, right? You reached your limit, and well, you're usually not allowed to reach your limit, right? Limits are asking the question, what happens when this occurs? What if I set x equal to this number? What if we set x equal to that number? For most functions, right, for a plain old linear function, you just allow x to equal 5, 10, 37, 1,000,006. Nothing goes wrong, right? Most of the time. And you can usually keep increasing a lot of functions. And we've often drawn our functions as we might draw our axes and draw a line there. And we always draw these little arrows on the end. You ever noticed that? We do it to the axes too. We say, hey, this keeps going that way. Even when we have polynomial functions, right? Even when we have now rational functions, We said it keeps going. What does that mean? I've always taken the shortcut. When you want to know the end behavior, well, there is no end. Plug in something really large, just to approximate it, just pretend. Plug in 1,000,000 for x, that's my go-to. Plug in 1,000,000 for x, and that's a close enough approximation of infinity, because can x ever actually equal infinity? The answer is clearly not, right? In fact, infinity itself is technically not a number, but a concept, okay? And so to try to plug infinity into a function here causes problems. You can't actually use it because you have basic math kind of breaks down, right? We're used to 1 + 1 = 2, something different. But infinity plus infinity equals infinity, and you can't really tell them apart that way. So you can't treat it the same as a number, which means we can't really let x equal to infinity, but we can get really close. We can look at, well, what's the trend? What's happening? This is getting smaller and smaller and smaller, closer and closer to that horizontal 0 axis. But does it ever technically touch? Well, no, right? In the same way that the x value never truly reaches infinity, the y value, the function value, never truly reaches 0. That's the idea of limits, right? The fact that you get really close, and for all practical purposes, you can think of it as equaling that, but it won't really get there, right? Our pencils are not fine enough to draw it in. What about dividing by 0? Right? Another common issue that comes up in math, hey, wait, you can't do that. But yet, here we have where we can plug in 0 into this function, right? And it causes all sorts of problems. It creates vertical asymptotes. But it can also create holes, right? And the holes are not nearly as jarring, the removable discontinuities. And so maybe you can get really close. Maybe you can, where did I have that drawn in? There it is, right? Where's the hole here? 5/2. You're not allowed to let x equal 5/2. But what if we got really close to 5/2? Right, 5/2 is 2.5. So what if we let x equal 2.49999? Would that be the same as 2.5? No, not exactly, right? Because the reason it can't be 2.5 is that if you were to plug it into here, you would end up with an actual 0 at the bottom. If I put 2.49999 times 2, then subtract actual 5, I wouldn't be left with 0. I'd be left with not much at all, but it's not actually 0. So it's technically allowed. But we recognize the closeness of those numbers. And I think limits are taking another abstract step away from the hardcore math, if you will. Right? We're used to math being very exact, very specific, correct or incorrect. And there's often not a lot of room for interpretation. There's not a lot of room for the human intuition to be like, yeah, but I understand it to be this. It's like, no, it's exactly is or is not. Whereas limits are bringing a little bit more of that human brain power into it. We're letting our intuition, our general understanding override the specific answer, right? We're letting ourselves, well, okay, technically it's 2.49999, but it's so close, right? We have enough experience now with rounding numbers that when we see this, we want to naturally round it up to 2.5. Or maybe you'd say, well, it's definitely under 2.5. Maybe we'll round down to 2, right? But it's very natural for us now to round it to 2.5. right? And this is something that spurred Newton in his development of calculus, asking that eternal question of, yeah, you're not allowed to do this, but what if we could? What if we did it anyways? What if we thought of a way to do this, to divide by 0, to let x equal infinity, to let x equal 2.5 when it otherwise shouldn't, just to see what happens when it does. Right? Do I actually break math? Well, okay, I would be left with dividing by 0, and I have no way to compute that. But in the same way that I know that 2.499999 is really close to 2.5, I can say, well, it's almost 2.5. I could plug that into my function, plug it into your function here, and actually get a y value here. And it's going to be whatever it is, 0.99999. Oh, I could just round that up. And so I know intuitively what it should have ended up as, right? Once I removed that removable discontinuity. Right? So the eternal question then is, well, how do you know when close enough is actually good enough? And that's what limits are going to tell us. And we're going to have tools in calculus that will give us an exact answer to this final question here. What is good enough approximation for a limit? Until we have that, we have only two tools available to us. We can do, as I've done there, plug in really close numbers, go out to an extra tenths, hundredths, thousandths place decimal, and you're going to have to use your own judgment on what is good enough there, right? Do we need 2.49999? Is 2.49 close enough for most of us? Probably. Maybe just one extra decimal. But if you really want to know for sure, right, go an extra decimal, go another decimal. Make sure it's not a coincidence, right? You check a couple of values. And we've done this before. We did this calculation when we were dealing with going from secant line to tangent line. We calculated the slope of between 2 points that got closer and closer together. We found the slope from, instead of at 4, we found, well, from 3.9 to 4.1, and then 3.99 to 4.01. Right? We got closer and closer together. That was limits. And so what we're going to tackle tomorrow and then continue on Monday is finding limits algebraically. This is the second way. Not by plugging in really close numbers, but by dealing with the removable part of the removable discontinuities and saying, okay, would have resulted in this, but can I simplify this function? I keep switching back and forth. Can I simplify this function in such a way that would allow me to approximate what this should be? I think I have the work, right? Almost. Right? But if you factor this guy out and remove that removable discontinuity, right, up here, your numerator, 2x minus 5, denominator has 2x minus 5. So if you reduce those, what are you left with? You're only left with x plus 2. Right, so the function around that point resembles x plus 2. That's how we got our asymptote there, right? It's just y equals x plus 2. So it should be 4.5. We're not allowed to actually equal 4.5, so you'd get 4.499999, right? That's the difference. Once the function is y equals x plus 2, now I can put 2.5 in exactly and get my exact answer. Any questions so far? No? All right. Then that's going to do it for words from me, I'm now going to turn you to the musical portion of today's topic. And I want you to listen closely to the lyrics of what he's describing this process is like, what a limit then means for calculus. You are confused. Okay. Keep working on it. Listen to the song, see if that helps clear it up. We'll do some actual exercises with it, because I know I'm being very abstract right now, because we're not actually working anything out right now. We're just talking about the ideas here. So maybe it'll cement itself more tomorrow. But what I want you to do for today is just big picture. What are limits? Why are they useful? Why do we use them in math and calculus specifically? And that's what you're going to answer on Google Classroom today. So I have the song here. Let me switch to Google's version as well.
If there's no value at this point, it's fine. Find a value anyway. 'Cause I know if I come from the left or the right, if they need it, I will find that a limit's alright. A limit's alright. Sometimes I see that X approaches A. So X gets infinitely close to A. And I know if I come from the left or the right, close enough, I will find that a limit's alright. A limit's alright. His small epsilon's gonna have a small delta for sure. They get so small they can't get any smaller. Sometimes I see that X approaches A. So X gets arbitrarily close to A. And I know if I come from the left or the right, if they meet, I will find that a limit's alright. A limit's alright. A limit's alright. A limit's alright.
Okay, there's the song. So, what was he saying there? If I come from the left and the right, and they meet, the limit's all right. Well, talking about as X approaches A. And the notation for that is, we're talking about the limit as X approaches A. So we use that arrow, right? And you might have seen that usually with infinity as X approaches infinity, talking about end behavior. But we can generalize that to be any number as X gets close to, right? He said as X gets infinitely close to, or as X gets arbitrarily close to A. What happens? And I'll recreate the diagram they have there. Here is my x-axis, here's my function here. Right here is A. For this value right next to A, I have a value on the function. For this value right next to A, I have a value on the function. But at A, I have a hole, right? just like the other example. I'm not allowed to let x equal a exactly. But if you were to look at this and zoom out and squint your eyes, you'd be like, well, it's some number in between here and there, right? It should be pretty easy to intuitively understand what the number should be. Say that, right, give it a y-axis here, call it 3, right? So this is 3.1, this is 2.9. It's right in between the two of them. Well, it's got to be 3. Even though technically it's not allowed to equal 3, we can get really, really close and understand, oh, well, it should end up being 3 anyways. That's the idea, right? We got to deal with these discontinuities, particularly on the rational functions. That's why I said keep the rationals on the back burner. They are the great example here of where this happens. You get holes in the graph due to a rational function, and you're not allowed to equal the exact value. But you can get really, really close. Okay, does that help now? In a sense, yes. You're figuring out what the value of the whole is. Or that will be one of our goals. Okay? Again, we're not doing the calculation today. Tomorrow, yes, it's definitely going to be filling in the holes. What value should go in for the whole? If you want to think of it that way. But we can also look at when they go out to infinity. So it's one concept that covers both aspects, when it goes to filling in a hole and approaching asymptotes, right? If this was actually like a horizontal asymptote out here, we could say, oh, it's getting really close. It's not going to quite touch that asymptote, but it's going to, at some point, they're so close together, I can't distinguish them with my pencil. And at that point, I'd say, good enough. Think of it as if it was equal to, what would this be, 1 or 2, right? That's the idea. Is the limit the value of the whole? Yes, if you were to ask specifically the limit of f of x as x approaches a would be equal to, in this case, 3. That would be the answer. Yes. All right. Limit as it approaches infinity would be whatever this horizontal asymptote is. I said that up there is 3, so maybe it's 1.5. Right? I can't plug infinity in to my function. I'm pointing at my screen, right? I can't plug infinity into the function to get that number. I can't plug a into the function directly and get that number. As they stand, it would break. I wouldn't get answers. Oh, but if I take the limit, if I just get really, really close enough, it's good enough. And we can just round up from there. Okay, don't plug 3 in. Plug in 2.99999, or don't plug a in, right? Plug in a 0.00001. Oh, it's 3.0001. Okay, round it off. The answer is 3. We knew that, right? That's all we're doing. Close enough is good enough. That's limit. All right, now, your task for today is to turn all of that inwards, shuffle it around, repeat it in your own words back on Google Classroom. Okay? You explain to me now, what is a limit? What's it good for? And when you've done that, you're done for the day. That's it. We'll actually work out some of the computation tomorrow.